In this video, we are going to begin Chapter 3 and cover Section 3.1. So Chapter 3 is all about applications of differentiation. So all those derivative rules that you learned in Chapter 2 are going to be applied in this section, or in this chapter. Okay, so Section 3.1, using first derivatives to find maximum and minimum values, and also to sketch graphs. All right, so objectives for this section: find relative extrema, that just means relative maximums and minimums of a continuous function using what we call the first derivative test, and also to use that information to sketch graphs of continuous functions. All right, so here are the definitions of what it means for a function to be increasing and decreasing. These are the math version of the definition, so you'll see math notation in here. Basically, increasing just means y values are getting bigger. Decreasing means y values are getting smaller. All right, this says a function f is increasing over an interval I if for every a and b, just numbers in that interval, where a is smaller than b, this says the y value at a is less than the y value at b. So if the y value at this first number is smaller than the y value at the second number, right, that means that the value got bigger, right? So it's increasing. For decreasing, it means for every a and b in the interval. So also implying here that a is smaller than b. If the y value at a, that's f of a, is larger than the y value at b, so the y value at this first number is bigger than the y value at this number, that means that the y values are getting smaller. So it would be decreasing. All right. So how do we use our derivative rules to identify those properties of a graph or of a function? So assume f can be differentiated over an open interval I if the first derivative of f is greater than 0, meaning positive. So if the first derivative has a positive value for all x in that interval, then that would mean that f is increasing. So first derivative positive means that the original function has an increasing pattern. First derivative less than 0, meaning first derivative negative for all x in the interval, then f is decreasing. So when the first derivative is negative, the function is decreasing. That's what we call the first derivative test. All right, next we're going to talk about what a critical value means. So the definition of a critical value for a function f is any number c in the domain of f for which the tangent line at the ordered pair c f of c is horizontal, meaning this tangent line is horizontal, that means the derivative would have to be 0, or for which the derivative does not exist. Okay, so here's kind of the shorthand version of what that says. C is a critical value if f of c exists and the derivative at c is either 0 or the derivative does not exist. Okay, so f of c exists, meaning that c is in the domain of f, but you're looking for places where either the derivative has the value 0 or the derivative does not have a value at all. If c is a critical value of a function, then the ordered pair c f of c is called a critical point. Okay. All right. Next definition is for what we call relative maximum and relative minimum. So the y value at c, f of c, is a relative minimum if there exists within an open interval I containing c such that f of c is less than or equal to f of x for all x in I. So the value at c is smaller than or equal to other function values in a close vicinity. We'll look at a graph here in a minute where it'll make a little bit more sense. All right, f of c has a relative max, okay, if there exists some interval I within an interval I, this open interval I2 containing c, such that the y value at c is greater than or equal to f of x for all x in that smaller interval. Right, so if this value is larger than or equal to all other y values in a close vicinity, right, then we would have what we call a relative max. So using the first derivative to find maxes and mins and sketch graphs. Okay, theorem 2. If a function f has a relative extreme value f of c on an open interval, then f of c is a critical value, meaning f of c either equals 0 or f of c does not exist. So this kind of ties together the definitions of relative maxes and mins to the idea of a critical value. All right? If the function has a relative max or min, then it must occur at a critical value. So if we're looking to find the maxes and mins, we have to first locate the critical values because they are related. All right, the first derivative test for relative extreme says for a continuous function f that has exactly one critical value, c, in an open interval from a to b, f has a relative min at c if the first derivative is less than 0 between a and c, and the first derivative is greater than 0 from c to b, meaning f is decreasing. First derivative less than 0 means decreasing to the left of c, and f is increasing to the right. There's some tables later in this PowerPoint that shows kind of how all this ties together, and it's a little bit clearer whenever we get to that here in just a second. I know these definitions are kind of hard to understand and written the way they are. All right, and then similarly, f will have a relative max at c if the function has a positive first derivative, meaning increasing on the left, and has a negative first derivative, meaning decreasing on the right. So if it goes up and then down, it hit a max in the middle, right? And if it went down and then up, it would have a min. Right? It would have neither a max nor a min if the derivative does not change sign. So if it has the same sign, meaning it's positive on both sides of c, or if it's negative on both sides of c. That would just mean it was moving up and then it's still moving up, or it was moving down and it continues to move down. That would mean no relative extreme value. All right, so here's kind of a summary of what we've just talked about that's a little bit easier to understand. It's kind of put together in this table form. Okay, so let's say this is the shape of the graph of f. Okay, this would mean a relative min point, right, at c. Notice on the left side here, the tangent line has a negative slope, and over here the tangent line has a positive slope. Okay, so we see visually the relative min, so this would mean that the sign, right, for f prime is the slope of the tangent line, is negative if you're on the left side of c, and notice the slope of the tangent line is positive, right, if you're on the right side of c. So it has to be the case that if the derivative is negative, the slope of the tangent line is negative, we would be decreasing, right? And then if the slope of the tangent line is positive, that would mean increasing. So if you go from negative to positive with the derivative signs, that would mean decrease to increase, right, on the interval. That always implies you're going to hit a min in the middle. Right? This one has a max at c, right? So we have a slope of the tangent line positive on the left of c, so the derivative would be positive. If you're choosing x between a and c, the derivative then is negative if you're choosing a value between c and b, right? Slope of the tangent line positive, slope of the tangent line negative, so you go up and then down, so increasing on the left, decreasing on the right means you have to hit a max in the middle. Okay, that's just the same thing those other two slides had talked about. All right, here's the case where there's no max or min. So if you were decreasing and you had a negative slope here, here's a critical value because the tangent line's horizontal, but then on the other side it continues to move down, right? The slope of the tangent line is still negative. So no sign change for f prime means negative on the left, negative on the right. So decreasing the whole time, no max or min. Right? Or if it was increasing on the left, then flattened out to 0, and then continued the increase on the right. In other words, a positive derivative on both sides of c, meaning increasing the whole time, no relative max or min. So it has to change sign. The derivative values have to change sign for there to be a max or min. All right, so we're going to do an example. Graph the function f given by this function, and then find the relative extreme. Okay. So let's suppose we're trying to do this without knowing any calculus, right? We could look at a graph. We could plot some points, figure out what the graph looks like, and analyze from there. Okay? So if we did it that way, this is what would happen, right? Choose some x's to plug them in, get the y values, plot the points. Or just graph it on your graphing calculator. Notice here you'd have to probably change your window to see exactly this. This only goes -5 to 6, but notice the y values here would have to be adjusted, right? Because you got to be down low pretty far, right, to -30 or -40 or so, and then up high to about 45. So if you adjust your window settings on your calculator to represent what you see here and then put that function in, you should see a graph that has this shape. So it looks like on this graph that right here we see this max, this relative max, right? So you see this horizontal tangent line, right? So from the graph it looks like that ordered pair should be a relative max. And then over here we have this relative min, right, with this horizontal tangent line right here, slope of 0 at this ordered pair. Okay, so that's just a visual. So now we're going to go through all the calculus stuff that we just talked about to show how that works. All right, so if we had to do this to calculate those exact values without having to use our calculator, we would start by finding our first derivative. So the first derivative of that function that we just looked at would be 6x squared minus 6x minus 12 by the power rule. Okay, then you take your first derivative and you figure out where does it not exist or where it equals 0. Okay, those are the two possible places for a critical point to happen. All right, this will always exist, right, because there's no x values you could plug in and get an undefined value, so we only worry about what happens when it equals 0. Okay, so if we set that equal to 0, we could divide every term by 6. That would leave us x squared minus x minus 2 equals 0. Then this will factor into x minus 2 times x plus 2, which would give us the solutions of x equals 2 and x equals -1. So these would be our critical values. All right, so those two critical values partition our number line into 3 intervals. Right, so if I plotted -1 right here and I plotted 2 here, we have a section on the left of -1, so that's the interval -infinity to -1. We have a section in the middle between -1 and 2, and then we have a section on the right from 2 to infinity. Okay, so that's like our x-axis. All right, so now we're going to analyze the sign of our derivative. Right, we're looking for where the derivative is positive and negative in each of those intervals. All right. So in our first interval, from -infinity to -1, they're calling that interval A, this test value just means choose a point in that space. So they've chose x equals -2. So when you plug a -2 into the first derivative equation, so you would go back to here, right? This was our first derivative equation, right? Any of these are equivalent, and plug it in, okay? So let's plug it into the factored form, into x minus 2 times x plus 1. All right, so if I plug a -2 into that, -2 minus 2 is -4, and -2 plus 2 is -1. So two negative numbers multiplied together is a positive. So that's how they labeled this as a positive. Okay, then you plug in 0. So back up here, if I plug 0 in for x, I get -2 times +1, that's -2. That's a negative number. So that's why they've labeled this interval as a negative. Okay, then they pick a number out in this section, right? They've chosen 4. So 4 minus 2 is a positive number, 4 plus 1 is a positive, and you multiply two positives, you get a positive. So they labeled that first derivative as positive. Okay, so according to the rules, sign of the first derivative is positive means that the function should be increasing on that space, -infinity to -1. Derivative is negative between between -1 and 2, so the function is decreasing on that space, and then it's positive again from 2 to infinity, so that means the function is increasing. Positive derivative, function increases, negative derivative, function decreases, positive derivative, function increases. Okay, all right, so by the first derivative test, okay, come back to here, think of if increasing is going up, right? And then decreasing means it's coming down. So if it went up first and then down, it had to hit a max, right? Over here, it was decreasing over here, so down, right? Then increasing, meaning up, means you had to hit a min, okay? So at this number, it switched from increase to decrease. So at x equals -1, there's a max. At this number, it switched from decrease to increase, which means at x equals 2, there has to be a min. So that's this page. F has a relative max when x is -1. So to find the y value, you plug that back into f. So f of -1, the original function that we graphed, gives you the y value of 19. So that ordered pair, -1, 19, would be a relative max. So even without looking at a graph, you could determine all of that, right, by using the derivative rules. F has a relative min, right? We already established that based on the derivative pattern at 2. So to find the ordered pair is you do f of 2. So you plug 2 into the original function. That would give us -8. So that ordered pair to -8 would be a relative minimum. Okay, so I know this is a lot of work. There's a lot to keep track of, but this is how you use calculus to determine properties of graphs. Okay. So here's another example. This one just asked to graph the function x cubed minus 27, x minus 6, and find the relative extrema from the graph. So you might have to play with your window a little bit, okay, but they show here the result that if you graphed this function on your calculator, right, this is not going to show up initially. Notice that this only shows up if you set your y window, right, to be like -100 to 100. So in a regular 10 by 10 window, you're not going to see very much. And notice their x window has also been shrunk down to smaller than what the standard would be. But if you play with your window a little bit, right, you should be able to get this view and see that at -3, right, it looks like there's a max. So to know that that's hitting at 48, you could just plug -3 into here, right? And then at +3, it looks like it hits the min, right? And to get the y value that they have there, which was -60, they would have plugged their 3 into this equation. Okay. The problem with doing it just by the graph and not analyzing derivatives is sometimes if those ordered pairs are not easy to identify from a graph, right, it makes it difficult. Whereas the calculus will always give you the exact answers, and they'll always be correct if you do it right. Okay, so let's try this one using the calculus steps. Find the relative extreme values for the function given by this equation. Okay, then after we've done it and found all that information, we'll use that to sketch our graph or to help us verify the graph on the calculator. All right, so first step 1, find the first derivative. Okay, so your power rule brings down the 2/3, leaves this x minus 2 inside, subtracting 1 from the power would give me a -1/3. Inside derivative is 1, so you don't really need it. Then the derivative of the 1 is just 0, right? So that's it. Right, so here, the 2 on the top, 3 on the bottom, this -1/3 power means this whole expression can be moved to the denominator and made into a +1/3 power, and the +1/3 power means the cube root. That's how this has been simplified. All right, next we would look at this derivative and look for where it doesn't exist or where f prime is 0. Right here, note that f prime does not exist when the denominator is 0, right? So if the denominator was 0, it would not exist. Well, that would happen when x is 2, right? So since the denominator is 0 when x is 2, that means x equals 2 is a critical value. Right? If I'm looking for where it equals 0, well, the only time a fraction can equal 0 is if the numerator is 0. But the numerator is 2, so there's no way it's ever going to be anything else. There's no x up there to affect it. Right? So f prime equals 0 when the numerator is 0, but since that can't ever happen, this will never equal 0. So the only critical value is the 2, right? That's what makes the denominator 0, and that will make the whole thing not exist. So 2 is our critical point. So you take your critical point, put it on a number line, partitions it into 2 spaces, left and right. Okay? So from -infinity up to 2, right, this first space, and then from 2 to infinity is the other space. So we're going to analyze f prime in both of those spaces. So we're going to pick a test value back here. So they picked 0, and they plug it into f prime. Okay, so take 0 and plug it in. This was our derivative. So if you plug 0 in for x, the top is a 2. This becomes the cubed root of -2, which is a negative number. So a positive divided by a negative is negative, right? So that's where the negative sign came from. That would tell me that the function would be decreasing because the derivative is negative. So the function's decreasing on that space. right? Then they plugged in 3, something on the other side of 2. So when I plug a 3 in, 3 minus 2 is 1, so that's cube root is a positive, everything else is positive, right? So they get a positive value right here, which would tell me that the function, since the derivative is positive, that the function is increasing on that space from 2 to infinity. All right, so the only critical point was 2, that was in the middle right here. So this was decreasing, moving down, and then increasing, moving up. So that would have to be a min, right? So it has a relative min at 2, and then to find the ordered pair, you plug it back into the original function f. So f of 2 simplifies to 1. So the ordered pair 2, 1 will be a relative min. Okay. If you graphed that function, this one, either by making a table or using your calculator, right, all that stuff could be verified. You see it decreasing, right, when x is smaller than 2, and then when it increases, right, the y values get bigger if I keep going from there, when x is bigger than 2, and the relative min that we can see on the graph is at the ordered pair 2, 1. Okay, here's another one. X to the 4th minus 8/3 times x cubed. Okay, so the derivative, 4x to the 3rd minus the 8/3 would stay, you'd bring down the 3, right? That third power would come down 3, keep the 8/3, x squared. The 3's cancel, so we get 4x cubed minus 8x squared. That's h prime. Okay, we need to know where it is 0 and when it doesn't exist. Okay, so it's always going to exist because there's no denominator to worry about making it undefined, so we set it equal to 0 to locate our critical points. So here we could factor out 4x squared. That leaves x minus 2. So setting those to 0 gives me x equals 0 and x equals 2. So my critical points are 0 and 2. All right, so now we go to our chart. Okay, so 0 and 2 will partition your number line into 3 spaces. The space on the left of 0, from negative infinity to 0. The space in between 0 and 2, from 0 to 2, and then the space on the other side of 2, from 2 to infinity. All right, so choose a point in this space. They've chosen x value of negative 2. Plug that into the first derivative, and it results in a negative number. That would tell me that the function is decreasing on that space. If you choose a number in this space, they've chosen 1. They plug that number into the first derivative, the h prime, and when they plug it in, they got a negative result, meaning that still the function is decreasing. And then from 2 to infinity, choose a number in that space. They've chosen 3. Plug that 3 into the first derivative, right? It's h prime. You get a positive result, so that means that the function h is increasing. So it decreases, then it continues to decrease, right? Even on the other side of that 0 that was a critical point, and then it turns around to increase. So since there's no sign change here, it was negative and still negative, so moving down and continued to move down, 0, right, that's where this one broke apart, is not a max or a min. There's no extreme value there. But at 2, right, the breaking point between these two intervals was x equal 2. It was decreasing, going down, and then increasing, coming up, means it had to hit a min. Okay, so therefore, at x equals 2, there's a min because of the sign pattern. So when you plug 2 into the original function h, you should get negative 16 over 3. So that ordered pair is where the minimum on the graph should be located. Okay, part of this is a lot of stuff to remember, and sometimes you're plugging things into the derivative, sometimes you're plugging it into the function, so you really have to pay attention. All right, so if you graphed that function on your calculator, this one's in a pretty normal window. See decreasing, flatten off to a critical point where it have a slope of 0, but then it continued to decrease, right? So there was no max or min there. And then here, it stopped decreasing and then increased. So there's the min, right, that we calculated. Okay. Next example. Find relative extrema for this function. Then sketch the graph. All right, so again, first derivative of 3 would be 0. You got minus, bring down the 1/3, so minus 1/3 x, subtract 1 from the 1/3 gives me negative 2/3. And we can bring this x to the denominator to make it a positive 2/3 power. The 3 is already on the bottom, so it stays down there. So we have a negative in front, 1 over 3x to the 2/3. So we need to know where g prime, this should say prime right here. I just noticed that. G prime, this should also be a prime. This is just a simplification of g prime. All right, where it doesn't exist or where it is 0. So g prime doesn't exist if the denominator is 0. That would be at x equals 0. And it'll never equal 0 because the top can't ever be a 0. I don't know what this is, just a kind of a weird looking math type equation. Okay, so it says g prime does not exist. It should say x equals 0. I'm not sure why it looks so strange. Also, there's no value that makes the whole thing 0, right? So our only critical value is at 0. All right, so the value 0 partitions the number line into two intervals, right? The left of 0 and the right of 0. So we're going to choose a test value out here. If you plug it into g prime, you'll get a negative. Means the function should be decreasing. On the other side of 0, on this interval, test point 1, plugging again into g prime gives us a negative result. So again, the function is decreasing. So we only had one critical point, right? But there was no sign change in the derivative on either side, so there is no max or min. So there's no extreme value for this function. It should just be a continuously decreasing function, right? Because it did not switch. Okay, here's the graph. That verifies what we just did. Decreases. Notice here the tangent line is vertical, so it has an undefined slope, right? That was our critical point. But then it continued to decrease, right? Which did not lead to a max or a min. Okay. This one, I know we've done lots of examples here, but that's just because this takes some practice. This one is a function that's going to require us to differentiate via product rule. Okay, so the algebra just gets a little bit longer, but concept and process is the same as the last several examples. All right, so to find the critical values, we have to find our first derivative. So by product rule, the first function is x squared. We multiply that by the derivative of the second. So the derivative of e to the negative x is e to the negative x times the negative 1 plus derivative of the first, so the derivative of x squared is 2x times the second function e to the negative x. All right, then they just factored. So notice both of these terms have at least a copy of x, and they both have a copy of this e to the negative x. So those things were factored out. So in this first term, if I took out one copy of x, all right, that would leave x. And I took this whole thing out, it just leaves a negative. So it leaves a negative x. So they've just written that right here. Minus x. And then over here, they took both of these things out, so the 2 was left. So really, if you left it in this form and you factored, you would have gotten negative x plus 2. They just rearranged it, right? Negative x plus 2 is the same as 2 minus x. All right, so next we need to figure out where this derivative is 0 or where it doesn't exist. Okay? All right, so it equals 0 when, so this part, so when x equals 0, right, or when x equals 2, this thing won't ever equal 0. That's always a positive number, okay? So that will never give me any solutions for my critical points, right? So it's just, so we can ignore the e to the negative x part. So you set x equal to 0, you set 2 minus x equal to 0, so 0 and 2. Okay? Use those values to divide up your number line, right? So if you plotted those on a number line, you got the left of 0, in between, and then the right of 2. So a test point in that space plugs into the first derivative, okay? This was the derivative. So if I plug a negative 1 into here for x, that's just going to be a positive number times a negative 1 and then times a positive number. So we're going to get a negative. So this says g prime with negative 1 plugged in, less than 0. That's just like putting a negative sign there, right? Plug in a 1 into here, you get a positive result. So g prime of 1 greater than 0. This means positive, right? So I don't know why they didn't just put a minus sign and a positive sign and a minus sign, but this means the same thing, right? Over here, plugging in 3 gives me a negative. So if I had a negative number here, the function's decreasing. This is a positive number, meaning the function increases, and then again, a negative number means it decreases. All right, so by the first derivative test, the change in sign, right, from negative to positive, right, so in other words, decrease to increase means we have a min, right, that min would occur at the 0. And then over here, it was increase to decrease, meaning you'd have to have a max occurring at the 2. Okay, so we have a min at 0, right, and then a max at 2. And then you would evaluate the original, back to the original function g at those numbers. So g of 0 gives me 0, so 0, 0 is your min. And then g of 2 gives us 4e to the negative 2. So that ordered pair would be your relative max. Okay, this would be very difficult to identify from a graph to know that exact number, right? You wouldn't look at, that's a decimal value, so you wouldn't know what the exact format would be without doing the calculus. Okay. All right, if you graph the function, all that can be verified. Decreasing on the left of 0, right, hits a min, because then it turns around and increases, right, briefly, and then right here, right, which this, from a graph, you go, oh, that looks like maybe it's about a half. Well, it might be, but my math lab is going to want the exact number, okay, and then decreases on the other side. So you'd have to do the derivative test information to know that. Okay. All right, so I know there's a lot going on here. The summary section here, just kind of overview of what we talked about. The function f is increasing if this is true, f of a is less than or equal to f of b, right? It's getting bigger as you move forward, meaning the slope of the tangent line is positive, right? Derivative means slope of the tangent line. Function is decreasing, right? If f of a is greater than f of b, in other words, the y values are getting smaller as you move forward, meaning the slope of the tangent line is negative. All right, using first derivative information, a function is increasing if slope of the tangent line is always positive, meaning f prime is positive. It's decreasing, slope of the tangent line is negative, right, meaning first derivative is negative. Critical value means function or a number in the domain such that the derivative is 0 or the derivative does not exist. That ordered pair is referred to as a critical point. Relative max point, higher than all other points in the interval containing it. Similarly, a relative min would be lower. Right? And the y value of such a point is called the relative max or min value of the function. Okay? Minimums and maximums are collectively called extrema, so that term extrema refers to both. And critical values are your candidates for possible relative extrema. First derivative test is used to classify them as a max, a min, or neither with the chart. All right, so that is the end of 3.1. There's a lot going on there, but it's applied concepts from ways you can use the derivative to look at function behavior.